Okay, so what I'm going to be doing in this lecture is I'm going to be going over a S-domain circuit analysis. So uh, I will probably do more than one of these because there are many problems that you're going to apply this to. But this is just at least just this problem here. And going forward into the future, I'll probably do many more different problems, but this is just one arbitrary problem. So S-domain circuit analysis. So to start with, let's go through an overview of what I'll be covering. So I'm going to convert from the T domain to the S domain. That's what you always are going to do when you start out these types of analysis. Then I'm going to use the S domain representation of the circuit to solve for the objective in the S domain. So, whatever your S domain objective is, or whatever your T domain objective is how you're going to manipulate what you're doing in the S domain once you form that equation. Then next, I'm going to convert back into the T domain, and I'm going to check the answer using a circuit simulator and MATLAB graph of a function, of the function that we end up getting in the end. So what in the world is the T domain versus the S domain? So the T domain is just simply the time domain. The S domain is a more generalized domain where you're going to be using what they call the Laplace transform. So I just simply refer to it as the S domain, which is a more generalized way of referring to it. And so that is that. So going on to the circuit of analysis that I'm going to be doing here. So this is the particular circuit that I'm going to be getting into, and for this example. And so what you have over here is you have a voltage controlled voltage source. Usually they use an acronym for this, VCVS, voltage controlled voltage source. Okay, so the amount of voltage that this voltage source puts out is going to depend on Vx. Well, what is Vx? Vx is just simply the voltage here with respect to ground in this particular example. And then I have R2 over here, R1 over here, and then C1 over here, which is just also just simply C. You can call it C1 or C. It doesn't matter because it's the only capacitor in this whole entire circuit. And then next I have my my source over here, which is 20 volts. So this is the circuit that I'm going to be analyzing. And then I have VA over here, which is going to be what I'm trying to solve for. So again, the analysis objective is to find the open circuit voltage at VA. Usually this is done for the Thevenin equivalent of the voltage, VTH, as you would know according to your textbooks. But simply here I'm just noting it as being the open circuit voltage at VA, which is what we are going to be solving all of this for. Okay, so next I am going to assign current directions. So you can assign current directions in any arbitrary way that you wish. There's no rule to this. You can assign it in any way that you want to. It is just that whatever you assign it to, you must remain consistent throughout your analysis. So you can't assign it one way and then halfway through your analysis you say, oh no, but I think it should be this way. No. Whatever you set up initially, it must be consistent. So I mean, it really doesn't matter. Like you could assign these any arbitrary way. It is just that however you assign them, you are basically anchored into that. So I say use something that's intuitive to you, that makes things easier for you. instead of something that makes things more difficult for you to see the intuition of. Okay, so that's what I have to say about that. But this is the convention that I created for this particular circuit. Now, in this circuit, I'm just going to be having current going into this node and coming out of this node, and then where else does it have to go? Nowhere else but here. We're talking about current flow, so we're going to need a, like a closed loop of some sort in order to have current going through. When like when you have a broken or not broken, but an open circuit, that's a better word for it. When you have an open circuit like this, then apparently there is no current that can pass through here, because this is open. The resistance across there is infinite, so therefore, there's no current going through here, so don't even worry about assigning a current there. So I just assigned the currents here, and so I have current 1, current 2, and current 3, and this is what I go with initially. This is how I set up the circuit. So elements in the S domain representation. So now, like this is in the time domain. Now we're going to need to represent these elements in the S domain. So 20 UT, well, what is 20 UT? Well, 20 UT, the envelope is a step function. And if you multiply that envelope by the 20 volt source over here, what it means is that at time equal t0, then this is turned on. That's all that it means. So to be more detailed in the schematic, it would be more detailed and more complete if I just simply had a switch here. Even though I didn't put that there, you're not always going to have that there. So it is just, I'm just pointing out that you need to make note of that this happens at time 0. In the simulator, it's going to happen at time 0, so therefore I don't need a switch. But it would be even more complete, even more complete if you had a switch there for U of t. Okay, so the 20 volt is multiplied by U of t in the time domain, and then you end up with 20 over S in the S domain as a S domain representation of that. Next, you have R1. Well, R1 is just stays the same as R1. Resistances just stay the same when you go from the T domain to the S domain. And so the same thing is true for R2. Then ZC is, which is the impedance of the capacitor in the S domain. That's going to be represented as 1 over SC. Next, we have Vx over 5 in the time domain. It's going to be represented exactly the same way in the S domain, Vx over 5. Going back to the schematic here, Vx over 5 is just simply saying, like in this schematic here, whatever it is, the value here that you have here across here, it's being multiplied by 1 over 5. So it gives you Vx over 5. And that is how that is, okay? And Vx is from where? From here. It's the same node here going to ground, which is here. So Vx is from this node down to this node. That is Vx. Okay, so current distribution at Vx. So according to the convention that I just arbitrarily made that I need to stick with, I have I1 plus I3 equals I2. Let's go back to the schematic. I1 plus I3 equals I2. That's how I come up with that. Okay, so I1 plus I3 equals I2. And then you'll note that in the schematic, okay, so you just go through this systematically, and you'll note that in the schematic, I3 happens to be equal to I2 based on the schematic itself. How is that so? Well, just look at it. I2 is going this way, it's going this way. Where else is it going to go? It can't go here because there isn't a closed loop. of any sort. So it just continues on here. So it's exactly the same as I3. Okay, it is 100% equal to I3. It's not divided in any kind of a way. So therefore, I3 is equal to I2. So then I can use that in order to make a replacement there. I know a lot of people say make a substitution. I don't like the word substitute because it kind of communicates something that I put in place of it, that kind of like is not as good or something like that. Like a substitute teacher, it's like it's not your real teacher. Your real teacher is the one that comes there Monday through Friday. If you're in grade school, K through 12. And when you say a substitute teacher, it's just something as a patch-in just for the day. So I don't like using that word substitute. It's actually a replacement. So I replace I2 with I3 there. And then, of course, that gives you I1 equals 0. When you relocate I3 to the other side, I3 minus I3 is going to give you 0. So I1 equals 0. So what about I1? Well, I1 is given by 20 over S minus Vx divided by R1. And then when I multiply R1 by 0, I get 0. Then I'm left with 20 over S minus Vx equals 0. Then I have 20 over S equals Vx when I bring it over to the other side. This is equation number 1 in my analysis here. Next, voltage distribution at the closed loop. Now, what is the closed loop? Let's go back over to this. The closed loop is here. Okay, I'm referring specifically to this loop here. I could call it loop 1 or whatever I want to call it, but it's this loop right here. So with that being the case, at this closed loop, Vx over 5 equals VR2 plus Vc. Let's go back to it and check. So I have this voltage, then I have current going through here. That's one voltage drop. Then I have the current still continuing on here. That's another voltage drop. And so this voltage is equal to these two voltage drops. That's where I get that from. So Vx over 5 is equal to VR2 plus Vc. And so we start breaking that into its components and expanding there. And so we have I2 times R2 plus I3 times Zc. Now again, note that I3 equals I2. With that being the case, go ahead and make a replacement, or maybe you can call it a substitution. But I'd say replace I3 with I2 because you're not going to go backwards. You're replacing it. So replace I2, or you replace I3 here with I2, and then you get this expression, Vx over 5 equal I2 R2 plus I2 Zc. Then Zc is equal to what? 1 over Sc. Next, you're going to factor out I2 from that expression, and then you're left with R2 plus 1 over Sc on the right side there. Next, you have Vx over 5 equals I2, and once you combine this expression, then you get this expression, which is Sc R2 plus 1 over Sc. Then you're going to relocate this expression, this factor, over to the other side, to the left side of the equation, and then you end up with this. So now you have an expression telling you what I2 is. Okay, so that becomes equation number 2. So now what I'm going to do is I'm going to combine equations. I'm going to combine by putting equation 1 into equation 2. And when I do that, then I end up with, let's go back to it. equation 1. Let's take a look at that. What is equation 1 again? Equation 1 is 20 over s for Vx. Equation 2 is just an identity for I2. Okay, so where I had equation 2 here, remember, Vx is what? 20 over s, right? Vx is equal to 20 over s. So in equation 2, I'm going to put 20 over s there. So see the Vx here? I put 20 over s. And that 20 over s is over 5. Then I'm going to continue to try to simplify even more. And then I get, 20 over 5s. And then that reduces to, like you have s here and s there. Those cancel out. 20 over 5 gives you what? 4. You multiply the 4 by the c. And then now you have an expression that does not include Vx for I2. So that's another step closer. Okay, so you have I2 equals all of this. These are, at this point, C and R2, those are knowns. Okay, so next, let's take a look at voltage distribution at VA. VA equals Vx over 5 plus Vx minus V of R2. Let's go back to the schematic here. What I'm saying here is that Vx over 5, and if I take that and I add in V of R2, and then I add in Vx, so I have Vx here from there to there, plus Vx over 5, and that should be equal to V of R2 plus VA, but I'm making it just, I'm subtracting it here. So Vx plus Vx over 5 minus V of R2 should be equal to VA. Okay? Or equivalently, I could say Vx plus Vx over 5 minus, or I could say, okay, I could say Vx plus Vx over 5 equals V of R2 plus VA equivalently. Either way, I'm still going to end up with the same equation. And so let's go back over to where we were before. Voltage distribution at VA. So we have VA equals Vx over 5 plus Vx minus V of R2. And so now I start to break that into components here. I2 times R2. And we have something for I2. Remember that from equation 3. Okay, so I'm going to combine this expression here, Vx over 5 plus Vx, and then I get this, and then that gives me 6Vx over 5 minus I2R2. And I'm going to use Vx equals what? 20 over S, which is equation 1. With that being the case, then now I have 6 times 20 over S, okay, because that's what Vx is, 20 over S, and continue to simplify that, and then I get 6 times 20 over 5. Even before I multiply that in, let's further simplify that. 20 over 5 gives you 4. 6 times 4 gives you 24. And so we have that expression. Next, I'm going to use equation 3 for I2. That was 4C divided by SCR2 plus 1. Then I put that in place. And I keep going, and we have 24 over S minus 4 times C R2, on the top here, and still have the denominator, the bottom there, as the same. So then I'm going to take that and combine this expression to get a total expression for VA. I'm going to continue to simplify. So here I have 24 times, in parentheses, SCR2 plus 1, and outside of the parentheses, minus 4 SCR2. All that's being divided by this, which is S times the parentheses of SCR2 plus 1. Then when I distribute this inward here, then I get this expression, and that is just 24 SCR2 plus 24 minus 4 SCR2. So these are like terms. I have what? SCR2 here, SCR2 there. They only differ by their coefficient, which is 24 versus a negative 4. Those are like terms. Add them up and you end up with 20 SCR2 plus 24 divided by S times what's in parentheses, and what's in parentheses is SCR2 plus 1. That gives you VA. I go ahead on and I further simplify by putting in values for R2 and also for C. C is half of a farad, which is 0.5 farads, half of a farad. So VA now becomes this, and I just continue to simplify by putting in these numbers. People refer to this as plugging in numbers. That just doesn't sound completely correct to me. I don't plug in numbers. What I do is I replace parameters with their parameter values, I would say. So go ahead and put in that replacement there, and then you end up with you have 20s times half of 20 gives you 10. Then you have 24 here, being added to that on top here. And so with this on the bottom here, you have S times half, which is S over 2. Then you can draw that half out, and it all has to make algebraic sense. If you were to distribute that half back in, you still get half here, but then half of what gives you 1, half of 2 gives you 1, so it has to make algebraic sense there. And so you end up with this expression, and then you factor out a 2 from these two numbers here. 2 times 5 gives you 10. 2 times 12 gives you 24. So next, then what does that become when you have half in the denominator? 2 divided by 0.5 is going to give you 4, So that's how you get a 4 there on the top. And so that is your expression for VA. However, you're going to need to simplify it some more by doing partial fraction expansion. It's not that this expression is wrong. It's absolutely right. All of these expressions are right. It's just that you want a form that gets you to the point where you need to be. And this form is getting closer, but it's not all the way there yet. So you're going to use partial fraction expansion, because then when you go to look up your Laplace transforms in a table, then it's going to need to be in a certain form in order for you to back convert it from the S domain into the T domain. So you're going to need partial fraction expansion to do that. And so you have your 4 times 5s plus 12 on the top, parentheses there. And so that the denominator is going to be broken up into S and then S plus 2, with A on the top for S, B on the top for the S plus 2. And you're going to figure out what is A and what is B. So using partial fraction expansion, it comes out to be that once you multiply your S on both sides here, you have this on the left side, and you have A by itself, and you have B being multiplied by S, And once you make S 0, then you eliminate this equation, and you are left with just A by itself. And when you set that equal to 0, of course, which would eliminate the B expression, on the right side. At the same time, it gives you an expression on the left side. And so with S equals 0, you have A equal to 24. You use the same type of procedure in order to derive B. So you multiply by S plus 2, and then you're left with, B by itself and A over S being multiplied by S plus 2. When S plus 2, when you put negative 2 in there, it's going to make this 0, and it's going to eliminate this. But of course, you have to maintain your consistency, and S must be evaluated also at negative 2 on the left side for this situation. Once you evaluate this expression with S equals negative 2, you get B equals negative 4. Okay, so finally we have that VA equals 24 over S minus 4 over S plus 2. And that is your final expression still in your S domain. Now when you go into your Laplace transform, going from the S domain back into the T domain, then you have 24 over S. You're going to take that, you're going to look this up on a table because those transforms have already been mathematically related and done for you, and they're going to list it on a table of transform pairs, where these pairs are the most typical pairs that you get, and there's more and more and more, I guess you can say, kind of like research that you can do specifically to S domain versus T domain transforms and transform pairs. Probably won't be anything that you will typically use, but nonetheless, that's kind of becomes its own branch of math. But they do list the transform pairs that you will use most typically. And so when you look that up on your table, you get 24 over S, and that's going to go and become, in the T domain, that's going to transform to 24 times U of T. Remember, U of T is just simply a unit step function that it says basically this is when things start, so that's your unit step function. It's multiplied by that. And then what about the other expression over here, negative 4 over S plus 2? Well, that becomes negative 4 e to the negative 2t, and it simplifies to that. So make sure that you append U of T, since the source envelope is U of T. So the source is going to dominate when everything starts. In this particular circuit, there's only one source, so it's going to dominate when everything starts. So everything is going to have to be multiplied by U of T accordingly, because nothing actually starts. None of the action starts happening until the source is switched on. So everything has to be multiplied by U of T, including this other expression here. So you have your negative 4 e to the negative 2t being multiplied by U of T. So now you just simply put it all together in the time domain, and your final expression is that VA equals 24 minus 4 e to the negative 2t, all of that in parentheses being multiplied by U of T. And so basically that is it for the derivation of what VA will be, going through the circuit and analyzing it in this way. Next, what I'm going to do is I'm going to simulate this and take a look at the circuit simulation and compare it to a very simple MATLAB script, and make sure that the two match up according to what I put in here, like the VA expression is what I'm going to put in MATLAB, and then I'm going to compare that to the circuit simulation and see whether or not there are several values that agree with each other within reason, within at least 1 decimal place of precision. It just depends on how many, I guess you call it like what the resolution of your simulation or what the resolution of your MATLAB script is. I mean, if you have a really high resolution, then you can have, several decimal places of precision. But, for the purposes of, like typically, generally, I'd say 2 decimal places of precision is definitely good enough. I mean, and you don't need to really go beyond that. But at least 1 decimal place of precision, typically, I would say, is what you really need. In other words, if you get, like if you get 4.1, 4.12, and then something else says 4.13, then that's good enough as far as I'm concerned. 1 decimal place of precision with doing things like these, because you're going to be able to see it overall anyways. I mean, you can get more decimal places of precision, but it's just that you're going to have to be more precise on where you place cursors, and you're going to have to increase the resolution of both your simulation and your MATLAB script in order to do that. And you can. I'm not discouraging that. I'm just trying to, make a good balance between what's necessary for verification and what's overdoing it. So it's actually a balance between being a perfectionist versus being more practical about what you're doing. Okay, so let's go ahead on and get into that next. Okay, so I'm going to very briefly just go over my MATLAB script that I have here. So I have here clear, CLC, close. So I'm starting off new with my variables as well as my graphing window. E equals EXP of 1. You don't have to use this, but I just use it in order to just be able to get E to be a constant itself in my script. Next, I have 2 equals 1 over RC according to our equation here. And so, therefore, 1 over 2 equals RC. Let me correct that. Therefore, that's just spelling. Okay, so therefore, 1 over 2 equals RC, which is equal to tau. Okay, so again, 2 equals 1 over RC, and therefore 1 over 2 equals RC, and RC is equal to what? Tau. Tau is the time constant, and we want to graph that over 5 time constants. This is what tells you what makes sense in order to see this response. So you graph it over 5 time constants, and the time constant tau itself is equal to what? RC. And well, what is RC? The RC time constant equal to? It's equal to half. So 5 times a half gives you 2.5. 5 over 2, 2.5. So you're going to graph it over 2.5 seconds in this particular example. Next, I just put here again, for my script. I have to use it in my script, so I have to put it there. Tau equals half. Then I'm going to use a linear space, from 0 up to 5 tau, and I'm going to use 500 points. Again, this is resolution. You can use more if you want to. If you want more precision in your verification check here, if you want, I just figure it's just pretty much totally arbitrary. I think about 500 points of data should be pretty good. Okay, but you can use what you want. Next, VA, according to our equation, was what? 24 minus 4 times e to the negative 2 times t. I'm going to use that there. Then I'm going to plot that t versus VA, and I'm going to have my grid on. So that is my MATLAB script, and then I'm gonna plot that, and I'm gonna compare it to my circuit simulator plot. Okay, so here's our circuit, and let's go ahead and do a simulation of that. I'm gonna go to transient, and I'm going to say 2.5 seconds there for t-stop value. And then I'm going to output, first of all, just to clarify and clear things up. Remember, in the analysis, I said Vx was equal to 20 over S, which in a time domain equals 20 U of t, in other words, when it starts. So in other words, Vx should never change from 20. Let's see if that's true. So this is what I get. And according to that, that's absolutely true. Vx starts at 20 and remains at 20 throughout this analysis here. So that checks out good. That was Vx. Now, going back over to VA. Let's go ahead and run that. What do we get? Okay, we get this type of curve that we get. Now, I'm going to now start to compare that with my MATLAB script, about 0.5. Let me go ahead and tell the cursor, give it an x value of 0.5. And that gives me a y value of 22.53 approximately. So let me go ahead and run my MATLAB script. The window is, it's going to be scaled, like the shape of it is different, so it may not appear to be the same thing, but let's go ahead and take a look at some values. Like if the aspect ratio of the window was exactly the same, it would give you, something that looks exactly the same. But let's look at the values, which is, numerical quantities here. Okay, so 0.506, we have 22.55. This is 22.52. That's good enough. Let's see if we can go a little lower there. Have 22.53 here. That's approximately 22.53 there. So that checks out very well. I have no complaint with that. Next, let's go on to 1. These are arbitrary points. You can choose your points, as you wish. And at 1, have a value of 23.46. Let's go over to this here and take a look at the cursor at 1. 23.4587. That agrees. Let's go on to 1.5 approximately. And I have that value there. 1.5. What do I get? I get 23.8 in my simulator. What do I get on my MATLAB script? I get 23.8. That checks out good. Next thing over, I'll say 2. And what do I get there for 2? I get 23.93 approximately. What do I get here? 23.93. And then I'm going to go all the way to 2.5. What do I get here? Well, I can just slide that over to 2.5 because that's the end of my simulation data. I get 23.97. What do I get there? 23.97. And let me go all the way back down to 0. I get 20 for time equals 0. What do I get when I go all the way back down to 20? Let's say cursor, x value 0, I get 20. So all of these values check out for 0, 0.5, 1, 1.52, and 2.5. So we can be very confident that the equation that we just got matches up to our simulation. And so that's basically it. The only other thing that I want to point out here in this simulation is that the initial value on this capacitor is going to be at 0. Okay, so initial condition for the capacitor is going to be 0 volts. And other than that, you know, the only other question would be like, why go through all of this S domain analysis in order to do this? Well, it's in order to avoid the time-based equations, which are differential equations when you have capacitor in your circuit. If you have a capacitor in your circuit, then you're going to get into either derivatives or integrals, and it is to hopefully ease that and make it easier to solve by using an algebraic expression in the S domain, as opposed to keeping it in the time domain and solving it with either differential or integral type expressions. So that is it. The circuit checks out well, and then that is the type of response that you have at the terminals of VA with respect to ground. So that is it. Hopefully this video was helpful for you. Thank you for watching, and have a nice day.